Hi, in today's example, I'll be doing the problem of a thin rod with a fixed end and at the other end an applied load. I'll be solving this in COMSOL 4.3. So I'll be doing this model in 3 dimensions. So we select 3D here, select next. I'll be doing the solid mechanics module, so I'll add that to my physics. You see the dependent variables automatically come up. First, the field displacement of u, v, and w. I'll hit next, and I'll be solving it in a stationary form. Hit solve, or hit final. So I'll begin by defining some global variables. So I'll choose parameters. So for the name, I want to define the radius of my beam, which I call radius rod, and that'll be 0.01 meters, about 10 centimeters. And I put brackets for the units and then recognizes it. And the length of my rod will be 1/2 meter, and the boundary force I'll define to be minus 100 newtons. Okay, so these are useful later on if you want to say run kind of an optimization problem and you want to change the radius of your COMSOL without having to redefine it every time. So this is kind of a nice way to do that. Now under model 1, I'll be defining a function, the analytical solution of how much a displacement I should expect for a bent rod with an applied force. So I'm going to compare at the end the analytical solution to the numerical solution COMSOL provides. So the equation is 4 times the force times 3 times the length of the rod. I'm sorry, first the name, I'll call it deflect. Okay, now for the expression, it will be 4 times the boundary force times 3 times the length of the rod minus the displacement, which is capital X, times the displacement again, squared, and divide that by 6 times now this sequence here, mat1.enu.e, is just a way to point to where the bulk modulus is stored in COMSOL. So it's under mat1.enu section, and it's called the E value. Okay, and then I'm going to multiply by pi, and then the radius of the rod to the 4th power, and then enter. Now you see it's also expressed down here as well. It's in yellow because it's warning me that the units may not be correct, which is fine because I've checked this before and it should be fine. But if it was in red, that would mean that it wouldn't like it at all, and it would just spit out an error. So, and you would have to find the error, the issue before you can continue. But with the yellow, it'll proceed, just kind of giving you a warning. All right, so now I'll build my rod. So I'm going to choose a cylinder. Under radius, I'll use my parameter of my radius, and then the length. That's my length of my rod. And I'm going to point the main axis in the X direction. So 1, 0, 0 there. I hit build all, and there it is. Now later on I'm going to compare the deflection of this rod with theory. So just out of arbitrary, just to show you, I'm going to choose to compare the deflection along the center line. So you see here that this rod doesn't have a center line yet. So I can add one. and adding a line pretty much forces COMSOL to put nodes along the line, and it'll solve for the equations for those points. So it'll be a little bit more accurate solution. Okay, so I'll right click for geometry, and under more primitives I'll add the polygon here. I'm going to add a linear function. So this starts at point 0, 0, 0, and I want it to go through the center of my rod. So along the x-axis, the length rod. So I'll build that, and you see that a center point started, was inserted here. Now this is actually in actuality a line across the entire rod. So you can see the inside of this rod by going to select boundaries. You just select one of these, and then you hit hide selected, and it hides it. And now if you zoom in on it, you can see the center line right there. Okay, just so you can see that for yourself. So now, we're going down the column here. We're going to add our material. I'll right click, open up the library, and I'm just going to choose copper since it's already in there. And you see here it lists all the predefined variables, and the three that it cares about for the solid mechanics module are the top three, and you see three green check marks, meaning that it has the necessary constants to solve this. If it will have a red X, then that means you have to input that value yourself. Okay, so now moving on to the physics. Okay, so it's assuming it's a linear elastic material, and it automatically gives you some boundary conditions and initial values. So we'll be adding a fixed constraint. So here again, the white represents body forces, while these bottom sections here represent boundary conditions, and you can also add point constraints as well, which is under this tab here. So I'll be adding a fixed constraint. I'll choose this face here, and I'll right click to add it. So that will be now fixed constraint, meaning that the displacement field will be 0. And since I'm going to apply a stress to the other boundary, I'll this time choose boundary load. Let me zoom out a little bit, and on the other here I'll left click on that and then right click to add it. Now the force, this you can add a stress, a pressure, or total force, whichever you want, but I'll be adding it in units of force. So I've already predefined my force to be boundary force, or BC force, and I already defined it to be in the negative z direction. Okay, so now the physics is sufficient. I'll just hit fine to get a little bit better solution, and then I'll right click and then hit compute and let it solve. Okay, and there you see the solution. Let me zoom out, and you see, if I just rotate it, you see kind of a skeleton or wire framework in black, and that just represents the original shape before the stress, and you can see that's already deflected. It automatically plots the von Mises stress, and you can see here the color axis or color legend, and you can kind of see where the most stress is along here and the least stress. Alright, and this is in 3D. Okay, so now we want to compare how much it actually deflects to theory. So I'll go under results, right click on results, and I want to add a 1D plot. Okay, so there it goes. And here again, there's many choices to put in this plot group, but I want to see a line graph. So I'll choose line graph. Now it's asking me which line, along which line do you want to see the data. And since I already predefined my center line here, I'm going to choose that line. And I'll hit boundaries because I want to hide this. And you see the center line appear. And now I'm going to choose, let me zoom in here. I'm going to choose the center line. I'm going to right click, and you can see that it added line 6 to that. And for my y-axis data that I wanted to plot, I'm going to go into solid mechanics, displacement field, and I'm looking for displacement in the z direction. Okay, so there it is, and it's in units of meters. Along for my x-axis, it's pretty much just the arc length data. Okay, so I'll plot that first, and there you see the displacement along the arc length, the center arc length, with the units of meters. Okay, so now so this is COMSOL's numerical solution. Now I'm going to compare this to the analytical solution. So on the line graph again, I'll choose again line 6. This time on the y-axis, I'll choose under the definitions deflect, which is what I called my function before. For x-axis, again, it's arc length. And this time I'm gonna change my coloring style. So instead of a line, I want it to be dashed. And also I want markers, so I'll choose diamonds, and I'll say choose 20 of them. Alright, so, and there we see the two plots on top of each other. You see the blue line, which is COMSOL's solution, and then we see the diamond green line here, dashed line, which represents the analytical solution. So you can see here that COMSOL did a pretty good job at calculating that solution. Alright, so, and say you want to, so this is just the displacement, but say you want to just see another quantity, physical quantity. COMSOL solves for a variety of them, and you can automatically, so you don't have to tell it, it'll just solve it for you. So say again we want to see the stresses now along the center line. So just by clicking under the y-axis data, you can see here that there's a lot of variables that COMSOL already solves for, like the energy, loads, material properties, reactions, strains, stress, and say I want to see the von Mises stress only along the center axis. So I click that and I hit plot, and there you see the stress along the center axis. So you can kind of play around with all this and kind of really get into detail of what's the physics that's going on in this problem. Alright, so yeah, so that's it for today, and yeah, thanks for listening.